Here is the mock solutions for your free response question. All right, for number 1, you're given some important information in your directions here. You're told, of course, this is the graph of f prime. And then you're also told that you have x-intercepts at -2 and 3 times the natural log of 5/3. And then the graph of g on the closed interval -4 to 0 is a semicircle, and you're talking about f at 0 is 5. So on this first part, you're asked about where maybe the function f, the original function, is possibly concave down. Now, based on what we have and what we've talked about in class, if we talk about f being concave down, then we know f double prime has to be less than 0. Well, that's great if I'm given the graph of f double prime. We can just look below the x-axis, but we're not. We're given f prime. So we have to kind of think about, well, how is f prime related to f double prime? Well, f double prime is the derivative of the derivative. Well, so if we talk about our derivative being negative, then that means the function that it's the derivative of is decreasing. Well, that's helpful because now we have the graph of f prime, and we can very quickly look up here and see, well, where is f prime decreasing? And f prime is a couple of intervals where it is decreasing. Notice here for the first one, we are decreasing from way over here, we were told, at -4 all the way down here to -2. So in this area here, I know my function is decreasing. And then I also know over here from 0 all the way out to the end of this, +4, my function here, f prime, is also decreasing. So if f prime is decreasing, then f double prime would be negative. So then that tells me where f, strangely enough, is concave down. So our intervals should be from -4 to -2, union, and then we pick back up over at 0, and we go all the way out to 4. So there's our interval where f is concave down. And again, concave down, first thought we should have second derivative 0, but we can't just use that and pick our answer. We're going to have to relate that to f prime. Okay, by the same idea, we need to talk about, well, over what intervals would our function f be concave up? We know f is concave up when the second derivative is positive, which would then we can conclude that f prime is increasing. And so looking at our graph, we see that f prime is increasing over the interval from -2 to 0. Okay, and looking at C, we need to talk about, well, where would f have a relative maximum? Well, f would have a relative maximum whenever, let's see, maximum, f would have to increase, then decrease. So if f is increasing, we know f prime is positive. And then up here, we'd have a critical point, so then f prime would be 0. And then we would start decreasing again, so then that tells me I need to look where f prime is now less than 0. So graphically, that's telling us that we need to look above the x-axis, cross the x-axis, and go below the x-axis. And notice all of that's going to be happening right here, and a lot of folks put 1.5 when we tested on this, but if we go back and look at our directions and information given about this value, we were told that that was 3 natural log of 5/3, which if you type that in your calculator, you do get approximately 1.5. But this is a non-calculator problem, so we have to be super careful here. So when we write our answer, and I need to erase, give me some room here. So when we're writing that answer, we have to stay conscious of what we were given. And so here we would have, F would have a relative maximum where x equals, and it's this intercept here, 3 natural log of 5/3. So again, be careful, pay attention to the information you're given. You shouldn't be on these free response questions just kind of trying to estimate a point there. Everything should be pretty exact. Okay, so for the next one, where would F have a relative minimum? So again, by the same idea, relative minimum would be looking something like this for F. So F would be decreasing, so that tells me F prime is less than 0. And then we have our turn, so F prime is equal to 0. And then F is increasing again, so here F prime is greater than 0. So graphically, we need to look for below, crossing, and above. So below, crossing, and above, well, looking over here at our graph, we don't have that anywhere. We have what looks like over here at -2, it kind of looks like we're going across there. We do high-five the x-axis, but we don't really cross, so we don't go back over and have a sign change here. So for here, we would say no relative min will exist for this one. So here, no relative min. Okay, for number 2, this is a review of something we did in the very beginning of the school year, and it looks like it's a good idea to review some of these. F is a function that is twice differentiable, so therefore we automatically realize, hey, we are continuous. So the function is twice differentiable for all real numbers. The table gives us values of F for selected points over this interval from 2 to 13. Now we need to estimate F prime at 4. So this estimate F prime at 4 means we need F prime at 4 is approximately. And this is back at the beginning of the school year. We talked about an average rate of change and how we can use that to estimate an instantaneous rate of change. So we have a rock, which is the slope of the secant line, so to speak, and we can use that for values super, super close to a point of tangency to estimate I rock. So let's look at our values that were given and see, well, where is 4 going to fall? Well, 4 is going to fall between 3 and 5, right? Duh. All right, so let's see. We need to show our work that leads to our answer. So F prime at 4, well, that's going to be our slope formula, F at 5 minus F at 3, all over 5 minus 3. So that tells me here, F at 5 is -2, minus F at 3 is 4, all over 2. And so this is going to give me -6 over 2, which you're welcome to leave that, or -3. So be careful with this. We can go down some interesting paths here, but really let's stick to the correct one, and this should be the layout for every one of these problems. All right, so for our next problem, Karen rides her bicycle along a straight road home from school, or from home to school, starting at home at t equals 0 minutes and arriving at school 12 minutes later. During her time interval, her velocity in minutes miles per minute is modeled by this piecewise linear function. This is great to see. If you have piecewise linear function, you can find your slope. You have great, awesome slope here. And so let's look at the very first one. Part A asks us to find the acceleration of Karen's bicycle at time 7.5 minutes. Indicate units of measure. So we need acceleration. We need to find A at 7.5. But the unfortunate thing is we're not given the graph of acceleration. We're given the graph of velocity. So if we pinpoint 7.5, that's somewhere inside of here. But remember, to get to acceleration, the acceleration function, well, that's going to be the derivative of your velocity function. And if we talk about derivative, we talk about tangent lines and their slopes. So really, at the end of the day, when it's all said and done, if I want the acceleration at 7.5, this is really, I just need the slope of that line, because here, if we're talking about acceleration, acceleration is the derivative of velocity, and derivative gives us slope of a tangent line. So really, is 7 acceleration here, A at 7.5, is equal to, well, let's pick two for sure points that we know here. So I know 7 and 0.3. So I know 7 comma 0.3. And then I also know 8 and 0.2. And so my slope changing wise, so 0.2 minus 0.3 over 8 minus 7. So that's going to give me negative 0.1 over 1. And then if we talk about our units, we have miles per minute. And then that's per minute, or you can do per minute squared. Either would be correct. Part C, shortly after leaving home, Karen realizes she left her calculus homework at home. What a great student. She is awesome. She turns around and goes and gets her homework. A, she did her homework, and B, she's going back to get it. At what time does she turn around and go back home? Well, we know that we change directions with velocity around times where velocity equals 0 and has a sign change. So those things, that's what we're looking for. So sign change. So let's see, up here, first turns around, so it looks like at time t equals 2 is when Karen turns around. Now a reason for my answer, because v at 2 is 0 and velocity changes changes sign around that value. So here we go from moving right to stopping and then moving left. So we've pinpointed where Karen turns around. All right, for the next question, here again we're given the graph of f prime, and we are asked about probably function f again, of course. So let's look and see. Again, graph of f, important. And f is a twice differentiable, so it is continuous. And we know f at 2 is 6. So for part A, find the x-coordinate of each of the points of inflection. So points of inflection, that's where my second derivative, and the second derivative equals 0 and changes signs. So how can I relate where the second derivative is equal to 0 and has some kind of sign change there? And we need to make sure that looks like the second derivative. Well, back up here, notice we're told that f prime has horizontal tangent lines at 1 and 3. So notice we have this and we have this. Well, if this is the graph of the first derivative, then this is where the second derivative would have to be 0. And so notice we also have sign changes here because my derivative goes from increasing to decreasing and decreasing to increasing here. So here we know what we're looking for. So let's think about this. When x equals 1 or 3, f prime equals 0, and f changes from, f prime changes, I think I'm going to run out of room here, changes, if we can get that to right, that would be fabulous, from increasing to decreasing, or vice versa. Okay, so hopefully that helps us to see, because a lot of times it's the same rules over and over. We're just applying them to the second and first derivative instead of the original function and first derivative. Okay, so at part B, at what value of x does f attain an absolute minimum value on the closed interval, and at what times does x attain an absolute maximum on the closed interval? And show your analysis that leads to your work. So here, as far as showing your analysis, we've really not looked at a major technique for that yet, but I do want y'all to look at the graph and see if we can pinpoint where we would have an absolute min and absolute max. So if we look at our graph, notice that we're talking about f, whereas it's maximum or minimum, not f prime. So here, if we look at our graph, notice all the way from starting here at -1 all the way to +4, f prime is negative. So f is decreasing from -1 all the way to +4. So we might say that f has an absolute minimum at x equals 4. Now, we've not really done any work to support our answers yet, and this is just, we're looking at it thinking, well, maybe that would happen there. And by that same idea, when we pick up from 4 to 5, notice that f prime is positive over that interval. So we might want to say that our absolute max occurs at x equals 4, or I'm sorry, x equals 5. And again, we've not shown our analysis for that yet just because we're not to that. This is just us looking at the graph saying, well, this might happen here. So later on we'll go into how to prove that, but for right now, this is enough. This is all we need. All right, moving on to the last problem we had. Let g be the function, and it looks like this. Find the equation of the line tangent to the graph of g at x equals 2. Well, all right, so let's see, at x equals 2. So the first thing we need, let's remember the equation for the line tangent that we used was y minus y1 equals m times x minus x1. And we know what x1 is. We're given that. There's our x1. Now we need a y1, so that's going to come from the original. So let's plug in and see what we get. G at 2 is equal to 2 times f at 2. Well, we need to know what is f at 2, and remember f at 2 was given to us. It's up here. F at 2 is 6. So we know we have 2 times 6, which is 12. So I know y sub 1 is 12. Now we need our slope, which means we need a derivative. So we need to look at g prime at x. And this is a product. This is x times f of x. So we need to do our product rule. So we have our first times the derivative of our second plus our second times the derivative of the first. So we have our values now. And now let's go through and see, well, what's going to happen if I plug in 2? So now we need to find g prime at 2. So let's see, g prime at 2. Go ahead and start a whole new line, g prime at 2. Don't put in equals here and plug in your 2. You'll lose some of your FRQ points. So this is going to be 2 times f prime at 2 plus f at 2. Okay, well, let's see. We have everything here, I think, to finish this. So that's 2 times, well, f prime at 2 is going to be -1. We can get that from the graph. If you look at your graph in your ordered pair, and then plus f at 2, we were told, is 6. That was given to us. So when we put all that together, it looks like our m value, or g prime at 2, is going to be 4. So now we're ready to write our equation. So we have y minus 12 equals 4 times x minus 2.